Good morning, everybody. Hopefully you guys are doing okay today. I would love to start with some green check marks. And if you had any questions from a few pages of the learning guide I left you guys with last day that you wanted me to maybe touch on before we just continue on with the notes. Today I want to look at some of the extra practice sheets I'd given you, and I'd also wanted to look at some covalent naming and just finish off section 4.2. So, perfect, Haley. If you have some questions, just fire them into chat. Go with page and question number or some reference because they're all in kind of tables. And we can go from there. And if anyone else has anything that comes up, just fire it in and we will just keep going. So kind of think of today as maybe just going over some practice and looking at some of the questions. As I mentioned last day, the questions that are in the learning guide don't really do a very good job of covering all the material that it's important to know for Science 10 chemistry stuff. So it's really important that you guys do go through some of the extra practice. First table in the practice, I think. Do you want to put in a page number, Taylor? Because I don't know if you're referring to the stuff we did a couple days ago on page 20 here, or if you're talking about 21 or 22 or along those lines. That would help me out. I see a few other people typing, which is good. Question 13, page 13, for sure. Page 1 of the practice sheet you assigned. Okay, so the extra practice you're talking about, I'll go through some of that. Page 12 in the learning guide, page 13. All right, it seems like there's a pretty good consensus on page 13. And then Anna, you're asking about page 12 as well. So I will go back up. Page 12 of the learning guide. All right, so Lewis dot structures is on page 12, and then I'll go through some on page 13 after. I didn't really do a ton of examples of Lewis dot structures. You guys usually have a really good idea of the Bohr models, so this stuff generally comes pretty easy, but I didn't do any, so I could see why you'd be confused. Let's see what it's hoping for here. Draw Lewis diagrams for the atoms and ions of the first 18 elements. So atomic number 3. All right, so if we're looking at element number 3 on the periodic table, glancing down at my periodic table, element number 3 is lithium. So the symbol for lithium is Li. And lithium is in the first column of the periodic table. So it's in the first group. So column and group are the same thing. And then it asks for the atom. So lithium is in the first column, so it should have one atom in its valence shell. It's just that easy. If it's in the first column, it has 1 dot. If it's in the second column, it has 2 dots. If it's in the 13th column, it has 3 dots. Lithium. Is lithium likely to gain 7 or lose 1? Same idea as the Bohr model. Well, lithium is likely to lose the 1. So if you are lithium and you've lost your electron, how many electrons do you have in your outer shell? You don't have any. You lost it. So your outer shell is empty now, and you have a charge of +1, or just the plus sign. I never really mentioned cations or anions, and I'm not sure it came up in the notes even, but it is kind of important. Cations are positive, and anions are negative. What's an easy way to remember that? Well, cat has the letter T in it, and T kind of looks like a plus sign, so cations are positive, and anions is kind of like anti. If you have an anion, it's kind of like anti, and anti is against things, so anions are negative. Just distinctions that chemists use to tell the difference between the things that are positively and negatively charged. Let's look at element number 4 is beryllium. That is in group number 2 or column 2 on the periodic table. You can see it there, element 4, second column. Symbol for beryllium is Be. And because it's in the second column, it's going to have 2 electrons in its outer shell. There's 1, 2. Is beryllium going to gain 6 electrons or lose 2? Well, it's probably going to lose 2. So if it loses 2 negative charges, it now has 2 extra positive charges, so it'll be positively charged. And that makes this a cation as well. Do you need me to go through more of these, or we kind of get the hang of it? I guess I could do boron, because that gets a little bit confusing. Boron's in group 13, symbol is B, and it has 3 electrons in its outer shell. It has a atomic number of 5, 2 in the first shell, 3 in the second shell. It's in column 13, that means its outer shell is going to have 3. And then boron generally won't form an ion, just because it's so close to the middle. I'm not sure what the answer says in the back there, but generally speaking, boron and carbon aren't going to form ions. Carbon is in column 14. It has 4. Yeah, Abby, sorry. I'm happy I did those two. So boron and carbon don't have the ions, because when we say, oh, are they going to gain or lose, they're right in the middle. And the way to notice on the periodic table is that there's no charge indicated in the top corner of those guys. So you can just write there's no ion. It doesn't form an ion. So boron and carbon, they won't form ionic compounds. They'll only form covalent compounds. How did you know it was going to gain 6 or lose 2? I'm still kind of confused. Whatever is lower, Taylor, so whatever is smaller. So when we look at something like well, all of these that we've done so far, like lithium had 1 electron in its outer shell. It's going to be easier to lose 1 than it is to gain 7. My brain fired up here this morning. So 1 is smaller than 7. Kind of like rounding, yeah, that's a good way to look at it. Except when we're rounding, you get to the middle. In math, if it's 5, you get 5 or greater, you round up. In chemistry, if you're in that middle ground, like the 5s and the 4s and the 3s, the elements just get really confused. Sorry, Taylor. A shell will hold 8 electrons. So the reason I chose the number 7 is because that outer shell, the valence shell in lithium, can only hold 8. That's the maximum it can hold. And when we're talking about Bohr models and Lewis structures, we're always talking about the outer shell. So if it can hold 8, it only has 1 in it. It's either going to gain 7 to fill the 8, because that's what it wants to do to become happy, is fill its outer shell, or it's going to lose 1, and once it's lost that 1, it just has its inner shell, and its inner shell's full. So that's where those magic numbers are coming from. The maximum number of electrons that a shell will hold. Okay, it's good. A lot of people are asking about page 13, which is just a continuation of the table from above. So you're just continuing on. I don't know, let's pick a few elements out of here. Let's pick element number 14, which is silicon. You see it there. Silicon's 14, it's a non-metal, just on the step. Silicon is in the 14th column. Black. So element 13 is in the 14th column. That's possibly a bit confusing. Its symbol is silicon is Si. And then we do some math. So it's in the 14th column. It'll have 4 electrons in its outer shell. And then it's not going to form an ion because it's right in the middle. It doesn't know if it wants to gain or lose. There we go. Let's do a couple negative ones, and then I'll do the question 13 on this page as well, because I know a few of you are having questions about that. Let's jump down to 16, which is sulfur. It happens to be 16, and it's in the 16th column, which is just a coincidence. I don't believe that was planned out. Sulfur is in the 16th column, so it'll have 1, 2, 3, 4, 5, 6 electrons in its outer shell. And then when we talk about the ion, it's going to have 1, 2, 3, 4, 5, 6. And because it only needs to gain 2 to have a full outer shell, a full 8, it's going to do exactly that, gain 2 electrons. Now, if I've gained 2 extra negative charges, I will have a charge of -2. Which makes this an anion because it's gained extra electrons. So one really interesting thing about Lewis structures with ions is if it's a metal, it's going to have an empty outer shell. If it is a non-metal, it'll always have a full shell. And that's just a general rule that works for all Lewis structures of ions. Are we supposed to draw the dots in the ions part? Did the examples have the dots? Oh, that's what I guess I was just saying. So because all the ones in the examples are metals, they'll have lost their electrons. But when we have non-metals, they're gaining electrons. So because the metals have lost the electrons, their outer shell's empty. When we draw the Lewis structure, there are no dots. But when we draw a Lewis structure of a non-metal, maybe I'll do chlorine as well. Chlorine's in column 17. So it has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's going to gain an extra electron to fill its outer shell. And now chlorine is going to have an overall charge of -1. There you go. So if you're gaining electrons, you need to indicate that in the outer shell. Whereas if you've lost them, your outer shell is empty, and you don't have to draw it in like that. I could see where that would have been confusing. It was on the slide in the notes, but apparently I didn't draw enough attention to it. All right, let's look at number 13 here. Draw a Lewis structure for an N2 molecule in the ionic compound Na2O. All right, let's start with nitrogen. So nitrogen is in the 15th column of the periodic table. So with its Lewis structure, it'll have 1, 2, 3, 4, 5. Now, this says N2, so we're going to draw another nitrogen here as well. And it's going to have 1, 2, 3, 4, 5. All right. Now we need to ask ourselves, how many electrons is going to make nitrogen happy? Now remember with Lewis structures, And in this case, we have two nonmetals, nitrogen and nitrogen. They're going to be sharing electrons. When we have two nonmetals or covalent bond, the electrons don't get transferred, they share. So nitrogen is looking to have 8 in its outer shell. So if I'm nitrogen and I share these electrons right here, how many will I have? We'll have 1, 2 at the top. 1, 2, 3, 4, 5, 6. Is that enough to make it happy? No, that's not enough. It needs 8. So I'm going to just erase the red numbers here. What if nitrogen shared another pair of electrons? What if it shared these bottom ones too? Now is nitrogen happy? So I have 1, 2, 3, 4, 5, 6, 7. Nope, that's not 8 yet, so it's still not happy. What if nitrogen now shared that last electron? Does that work? Let's count. We got 1, 2, 3, 4, 5, 6, 7, 8. So that nitrogen's happy because it has 8 electrons. It's kind of a weird situation here where nitrogen, I'm just going to redraw this diagram. Nitrogen has these 2 electrons up at the top. I'm going to put them on the side here. And same thing over here. And nitrogen forms what we call a triple bond with itself. So each one of those lines represents a shared pair of electrons. So if we do the count again, we have 1, 2 on the side. This nitrogen also has 2 on the side. And each pair of, each line, I should say, represents a pair. So this is 2, there's another 2, another 2. So there's 2, 4, 6, and then 7, 8 on the side. I will say that covalent molecules are kind of weird, and Lewis structures of covalent molecules are even weirder. They don't really make sense, and there's not a lot of rules that govern how they work. So it's not like I can say, this is how it's going to work all the time. You need to just do your best to try to wrap your brain around everything. Needs to have 8. They're sharing with one another. Can you make a picture that works? And unfortunately, there's not much more to it than that. Let's look at the compound Na2O, and then maybe we'll move on. We haven't spent a lot of time on covalent molecules. We will today. Maybe this will make life a little bit easier. Now, this says it's an ionic compound, so we know ionic compounds are going to form ions and electrons are going to be transferred. Generally speaking, we're going to want things to be kind of symmetrical. So I'm going to put the O in the middle and the NA's on the outside. How did I know to do that? Well, it says Na2, so that means there's 2 NA's, and then there's nothing after the O, so we just assume there to be 1 oxygen here. Now, we just drew sodium on the periodic table, or was one of the examples. And sodium will have 1 electron in its outer shell because it's in the first column. And it's going to get rid of that electron and have a positive charge. So each one of the sodiums will have a positive charge. Now, oxygen is in the 16th column, sorry. So we'll have 1, 2, 3, 4, 5, 6. And then each one of the sodiums is giving oxygen an extra electron. So oxygen has gained 2 electrons and will have a charge of -2. So that's what that compound's going to look like. You notice the difference between what I've drawn here. My nitrogen has these lines showing shared electrons. In ionic compounds, here, we don't share electrons. Electrons are transferred. I guess I could write that. And that is by definition what an ionic compound is. An ionic compound is where electrons get transferred to something else and they become an ion. They become charged. Whereas when we have something like a covalent compound, the electrons get shared. There's no charges to be drawn. No, you don't need to do the different colors. The only reason I did the extra colors was just to kind of show you that those red dots didn't always live with that oxygen. They were part of the ion, but they're not part of the atom of oxygen. So it's just trying to show you that those came from somewhere else to try to straighten things out. All right, was there anything else from the learning guide that came up that was kind of tricky or you didn't understand or I didn't go through that you asked up above? I just kind of missed your question. So we've gone a fair ways through chat here. Anything you wanted me to do in terms of the naming? We're going to look at a bunch of different naming stuff right now, and then we'll talk about covalence to finish off the class, and then you guys can do some work. No other questions? All right. What I'm going to do is I'm going to go to the extra practice. Maybe I'll just show you where that is in the course. All right, so if you're in the course, or you're in the chapter 4 section, you can see we have this guy right here, naming extra practice. So if you click on that, you're going to download it, and it's going to give you all the sheets I'm about to look at. Now, I said, none of it's required. I really want to change my mind on that and make you guys do at least a few pages, but I'm going to resist temptation. I'm hoping you guys will anyways. I'll go through a bunch of them today in class, so at least you'll have some of it done. The other thing that I didn't mention that's in here is, where did it go? There's a page here, it's called Build an Atom Practice. So if you're really kind of caught up in the idea of ions and protons, neutrons, how it all works to make an atom, if you're caught up in like the very beginning stuff that kind of builds onto everything, if you open this guy up, it takes you to another website, and there's this kind of like interactive page here that loads within the course. So you can go and build an atom. Maybe we'll just look at that quickly. What you do is you just drag protons and neutrons into the middle, and over here it tells you what the charge is, what the atom's going to be, and if I added an extra proton, it's going to go from hydrogen to helium. If I add another proton, it's going to become lithium, and then I can just keep adding neutrons, and it stays as lithium because protons determine the number element and the name of the element as well. So you can play through it and do a bunch of stuff with regards to that. And there's another one that's the same thing, but looking at the symbol on the periodic table is kind of a cool little simulation. Probably has a little bit more to do with grade 9 than it does grade 10, but you can add electrons and they'll go to the right orbits, and then you can put them. You can see that the first shell holds 2, and then you get more. It shows you when it's an ion or an atom. So I thought it was pretty cool. I put it in there. If you want to play around with it, it might be worth your time. All right. Taylor has another question, page 21, number 4, and then I'll jump into some of the extra practice, and then we'll talk about covalence, and then we'll call her a day. All right. So determine the formula for each of the following polyatomic compounds. So as soon as you see the word polyatomic, you know we're dealing with the polyatomic ion sheet on page 5 of your data booklet. I'm going to get mine out here. That was the one I included in the notes, and it is the list that's there for you to look at. You don't have to memorize them, they're there, so please don't memorize them. Be careful to use brackets only if they are needed. They're needed only if you have more than one polyatomic ion. So here we go. Sodium is Na, and sodium has a charge of +1. Bicarbonate isn't on the periodic table. This is where some of us are going to get really confused and try to find bicarbonate all over the periodic table, and it's not there, it's not there, it's not there. And then you're going to go to the alphabetical listing of all the elements, search for it alphabetically, it's not there. oh my goodness, Mr. Borden, there's a typo on your worksheet. And this happens all the time where students are like, Mr. Borden, this actually doesn't exist, you made a mistake. And I'm like, yeah, it does. And I feel really bad because they just don't know what's going on. So bicarbonate is on page 5 of your data booklet. It is, it's a polyatomic ion. So bicarbonate is HCO3. Maybe I'll do this guy in a different color for a few of these. And HCO3 lives together happily with a charge of -1. So there you go, sodium, bicarbonate. We need to combine these things together. You can think of crisscrossing the charges, you can think of balancing it out. If one has a charge of +1, that whole group, this group HCO3 has a charge of -1. So what is that going to look like together? You're going to have your metal first, and then you're going to have bicarbonate. And the 3 is part of that. It stays with it, and that's just kind of what it looks like. Next one, calcium. Ca is +2. Sulfate is not to be confused with sulfite, and sulfate is SO4. It has a charge of -2. So I'm looking at the charges. One's +2, one's -2. If you get really caught up in the crisscrossing of charges, you're going to write something like this. Ca2, SO4, and 2. And of course, we're going to put that SO4 group in brackets because it is a group and it can't be changed. We can't add S's and O's and everything independent. Unfortunately, that's wrong. We don't want to do that because we don't need 2 calciums for every sulfate or 2 sulfates. Because they have a charge of +2 and -2, they are happy to exist as CaSO4. Let's see if this next one gives us some brackets. Barium. Periodic table +2, I believe. What are you, barium? Oh, it's beryllium. Oh, barium's +2 as well. All right, so barium's +2. Phosphite is not phosphide. So phosphite, I see the ite, and I go to the periodic table. It is PO3. And that group, that one phosphorus and 3 oxygens together, they cling together, and they overall have a charge of -3. Now this is the first time we're going to have more than one group of the phosphate, or phosphite I should say. So we're going to have Ba, we're going to have PO3, and if you think about crisscrossing your charges, that's going to work here, but you're going to run into a bit of a problem. So Ba3, PO, and then you're going to drop a 2 down next to it. Now, you could imagine if I wrote Ba3PO32, that would be really confusing. Do we really mean 32 oxygens? No, we don't. We mean we have that group PO3 and we have 2 of that group. So this is where these polyatomic ions get a little bit confusing. We don't want 32 oxygens, so how do we demonstrate that? Well, we put a little bracket around that group. And because we put a bracket around the group, that means that there's 2 of that entire group. Now, I fully realize I talked about polyatomics last day and I didn't do any examples. So this is probably the first time you've seen some of these things, which is fine. We're going to spend some time today looking at it and continuing on with it a little bit further. So don't be all stressed out and be like, oh my goodness, I don't understand what's going on. We'll do lots of examples today. We'll make sure we're all kind of on the same page when it comes to this stuff. The next one is in the periodic table. Is that right? Common mistake. Yes, Ava, I will look at that as well. So ammonium, I look at ammonium and I'm thinking, okay, well, I can find that one on the periodic table. And this sulfur is S minus 2 charge. Ammonium, if you find it on the periodic table, I congratulate you because it's not actually there. So ammonium, if you'd looked it up on the alphabetical listing, it won't show up in the periodic table. Ammonium is that one example of a positively charged polyatomic ion. It is the one in the first column. It's by itself in that first column. It's the only positively charged polyatomic ion that you have to deal with in Science 10. And ammonium is NH4, and it has a charge of +1. It is the only positively charged one. So I'm going to write my NH4 group, and then I'm going to do my sulfur. And if you want to think of crisscrossing the charges, that works here. You're going to bring the 2 down, and that's going to look confusing. That's going to look like NH42. That's not what I mean. So how do I make some sort of distinction here? Well, I don't want 42 hydrogens. What I want is 2 groups of that NH4 molecule, or ion. And then there's 1 of this S, but I don't write in my 1s. So that's a bit of a tricky one. Ammonium comes up enough that you should be able to recognize it as being a polyatomic ion. Another really interesting thing, I might as well finish this off, is we can have 2 polyatomic ions bonding together. If we have ammonium and phosphate, they get phosphate, PO4 minus phosphate, PO4 minus 3. So we can have 2 polyatomic ions combined together, which is interesting. So we have NH4, we have PO4, and if I crisscross my charges, the 3 from the PO4 comes down here, and then I'd have a 1 here, but I don't need to put in the brackets for a 1. If it's just one group, I don't have to indicate that. So there we go. That's the first question. The first examples you guys have seen of this stuff. If you're still kind of a little bit lost, that's okay. We'll get there. There was one extra question that came up here. Could you also look at the last one for number 8 at the bottom of page 22? Name the following multivalent ionic compounds. So we see the word multivalent. These are ones with more than one charge. And Hg is mercury. Use the workspace provided, show how you determined that. All right, so what I'm going to do is I'm going to find mercury, Hg on the periodic table, and I'm going to see that mercury has a few possible charges, +2 or +1. And we're going to try to figure out if it's the +2 that we want or if it's the +1. Sulfur is always the same. Sulfur is always -2. That never changes. Sulfur is not multivalent. It is always -2. So if I look at the actual compound I'm given, Hg2S, I need to kind of figure it out in my head. Okay, there's only one sulfur here. So I always look to the nonmetal when I'm trying to figure out the metal, the charge on the metal. Sulfur is -2. So I have, in this case, -2 as a charge. What has to happen with the mercury to give me the opposite of that, a +2 charge? Well, I have 2 of them. So my mercury is going to be Hg and Hg. Now, if I have 2, and they both had, let's say, a charge of +2, which was one of my options, that together would give me a charge of +4. And +4 does not balance out -2. It just doesn't work. So I guess that eliminates +2 as being a possibility, but let's make sure. If I had mercury with +1 and mercury with +1, together those add up to -2, or +2, step ahead of myself, and I have equal charges, +2, -2, they balance out. So when I name this thing, I know I'm dealing with mercury with a charge of 1. And I need to indicate that with a Roman numeral. And this is sulfide. So name the metal, mercury, name the nonmetal, sulfur, change the ending to "ide", and then we indicate with a Roman numeral which charge we're dealing with. And in this case, it is mercury 1 sulfide. Hopefully that helps you out, Ava. That's definitely a tricky one. The multivalence going from the chemical symbols back to the names, they are hard. For sure they're hard. But after you practice a bunch of times, you get really good at it. You look to the nonmetal, figure out the overall negative charge, then you need to make the metal always have the equal positive charge. So what combination works? All right. And again, if you guys come into any problems with these examples from the learning guide later on, like next year or the following day, then by all means ask. Don't think because I spent some time going through it today, it's done, I'll never go back. If something comes up tomorrow, or I guess I won't see you till next week, but if something comes up, just say, hey, I'm having issues with this, let me, and I will be happy to do that for you. That's another good question. Sulfur with an F or pH, both are correct. It doesn't matter which way you write it. Just kind of depends on where you learned it. So you can do either one. Phosphorus, I think runs into the same problem. Sulfur, phosphorus. Those are the kind of ones that are spelled a couple different ways. Just depends on who's doing the work, I guess. And both ways are acceptable. All right. The extra practice that I asked you guys to do or look at, I'm going to do a few of them now, and then maybe we'll take a break, and then I'll do covalence. And maybe look at a few more, and then we'll call her a day. So the first page is pretty straightforward. I would strongly recommend you do number 1. This is a great chart that kind of has lots of sort of fundamental type questions about periods, groups, energy levels, and valence electrons. Kind of brings everything together at kind of a really basic level. So the period number is the row. I guess I could put that in here. Period is the same thing as row, and group is column. And energy level is shells, and valence electrons, you guys know what those are. So it's a bit tricky. Helium, that is in the first row. It's in the last column, or column 18. How many energy levels does it have? Well, if it's in the first row, it has 1 shell, and that shell can hold a maximum of 2 electrons. And how many electrons does helium have in its outer shell? It has 2. Helium's kind of one of the exceptions to the rule. So the rules kind of don't apply to helium. So it's just something you need to kind of think about, but it's small enough that you don't have to worry about it. The next one, you're like, whoa, it just didn't give me any information. It tells me something has 3 energy levels, and it has 3 valence electrons. Does that give me enough information to figure out what element this is? Well, we can skip it and come back to it, or we can just think about it really hard. If it has 3 valence electrons, that means it is in column what? If there are 3 electrons in its outer shell, do we know what column it's in? Yes, we do. We know that everything on the periodic table that has 3 valence electrons has to be in column 13. There's no way around that. So if you're in column 13, you have 3 valence electrons. Just that easy. Number of energy levels. Number of energy levels is how many shells it has. So if you have 3 shells, 1, 2, 3 shells, Remember, the first row has the first row has 2 electrons, 1 shell. Second row, 2 shells. Third row, 3 shells. When you fill a shell, you start again at the beginning. Fill a shell, start again at the beginning. Fill a shell, start again at the beginning. So if it's saying this thing has 3 shells, that means it's in the third row or third period. That's enough to help us figure this out. If we look at a periodic table, if we're looking in the 13th column and we're looking in the third row, what element are we dealing with? Remember, the first row is hydrogen, helium. The second row goes from lithium across to neon. And then the fourth row, the third row is sodium across to argon. So this is actually aluminum. So for sure, yeah, that's right. Tricky question, right? But it's not impossible to figure it out. The next one's telling you it's in row 2 and it has 6 valence electrons. As soon as I see 6 valence electrons, I know it is in the 16th column, or group number 16. If it's in row 2, it has 2 shells. It's just the way it works. So if you are in the second row or second period, the 16th group, you are oxygen. I'm gonna just kind of quickly look at the rest of this table and see if we can see some patterns that appear. Remember, it's called the periodic table because things happen periodically. Patterns are constantly repeated. So on this chart, if I ignore the next one, it says strontium, but I move on to the last 2 here, you can see that this says group number is 14. So if it's in group number 14, how many valence electrons does it have? Well, it has 4. And this is in group number 2. How many valence electrons is it going to have? It's going to have 2. What else do I know? If it has 3 shells, it's going to be in the third row. If it's in row 6, it's going to have 6 energy shells. So this is all just stuff I can know just because of the patterns that repeat themselves in the periodic table. And I'll leave it there for now. Maybe I'll throw some answers in next day and you can check your work with mine. Unfortunately, there aren't any answers here. Continuing the patterns in the periodic table here, if it's empty, I just look to the one below it because they're always going to be the same. Carbon's 4, silicon's going to be 4, nitrogen's 5, phosphorus is going to be 5. Everything going in groups is going to be the same. So that's what's really cool about the periodic table, is that everything in groups is going to be the same. There's no math involved here. There's no thinking. You just look above it. Okay, oxygen has 2, 4, 6. Sulfur is going to have 6. Chlorine has 7. Phosphorus, it'll have 7. So I just need to look below it. That's why we call these things groups, because they have similar properties. The exception here is helium, because it's in the first period or first row. It's only going to have 2 electrons because that's all it has room for. After that, it's full. And we move on to the next shell. So that's a really cool way to do these types of questions, understanding that things get repeated on and on and on again. Bohr diagrams, Lewis, you guys are experts at that stuff now. It just has some general names. I'm going to skip that. And I'm going to skip that. I'm going to go to the page that says Part 2, naming multivalent ionic compounds. So I'll just leave that up for a second. If you can find it, if you printed it, great. I want to go through some of these questions. because the mono or the multivalent questions can get a fair bit tricky. So I guess on the front page, we should remember that the Roman numerals are 1, 2, 3, 4, 5, 6, and 7. Those become really important when we start talking about the elements with more than one charge, multivalent metals. Now we've done a few examples of these, and remember we always look to the non-metal. That's going to help us the most. So if we flip to the back page, we can do a few of these examples. This page 4 here, how do I figure out what ion charge was used in a given formation? We look to the charge of the non-metal. That never changes, it always stays the same. Because it is always the same, the non-metal is always going to have a negative charge and it's never going to change. We can then balance it out from there. All right, so we're looking at page 5 here. I want to do a few of these. So I'll do 1 or 2 and then I'll give you guys some time to work through the rest of them. Chromium, I find chromium on the periodic table. It's element number 24. And its symbol is Cr. It has a few possible charges, but remember the 3 here means that I have a charge of +3. Phosphorus is always P, and it always has a charge of -3. So if I want to write the formula for these things, if I crisscross my charges, I'm going to get Cr3P3, but I know I only need one of each of them to balance out the charges, so Crp. That is what I'm looking for. What is this thing called? This is chromium. The 3 is important. And then instead of phosphorus, I change the ending to phosphide. So chromium 3 phosphide and Crp. Nickel, Ni +2, chlorine, Cl -1. How do I know it's nickel with a charge of +2? Well, the Roman numeral 2 tells me. So going from a name to symbols is really easy with multivalence. But when you're going backwards, it gets trickier. So nickel, nickel 2, and then chlorine changes to chloride. If I crisscross my charges, bring the 2 down, bring the 1 down, I end up with Ni with a 1 next to it, which I won't indicate, and Cl with a 2. That is nickel 2 chloride. That's what it looks like. All right, I'm going to leave these last ones up. I would like it if you would fly through them right now. I'll give you a couple minutes, and then I'll come back and I'll show you some answers for those. And make sure you're doing these, guys. I have another sheet of paper somewhere nearby. If we named these things like we do ionic compounds, we wouldn't be able to tell them apart. We would call this carbon oxide. That's what we'd call it. Name the thing on the left first, the thing on the right second, change the ending to "ide." CO and CO2 are very different things, as are CO, CO2, and CO3. These are carbon monoxide, carbon dioxide, and carbonate. They're all very different. So we need to come up with ways to name these things. So my rules. Name the thing that's furthest to the left on the periodic table first. So if you have 2 nonmetals, how do we know which one to write first? the one that's furthest to the left, the one that's closest to the metals, the one that's closest to the staircase. Rule number 2, name the second element, change the ending to "-ide." So this is just like we did with ionic compounds. The third rule is add the prefixes based on the number of elements present, but there are 2 exceptions to the third rule. When there's only one of something and it's the first element, we don't use mono. If there's one of something and it's the second element, we do use mono. And then the other exception isn't that big of a deal, but it's important to note that if you are adding mono in front of oxygen, it's not monooxide with 2 O's. It's written as monoxide, which is kind of weird because if you had something like 10 arsenics, like decaarsenide, you'd end up writing 2 A's. So I don't know why we don't put 2 O's with monoxide. They just don't. That's just how it goes. Carbon monoxide is scary stuff. Carbon dioxide is even scarier because we pump so much of it into the atmosphere and it's affecting our climate. All right, so those are my rules. Let's apply some of these rules to some examples and we'll see how we do. Before we do that, some of them have common names. And now that you kind of know a little bit about covalent compounds, what is dihydrogen monoxide? Is anybody familiar with what that is? Anyone ever seen dihydrogen monoxide before? Anyone ever encountered dihydrogen monoxide? Yeah, I'll go back to my rules. Let's go back to the rules right now. Then we'll get back to the... There we go. Sorry, I should have given you more time for those. I got carried away, got excited. Just want to move on. Ava, you are right, it's water, H2O. While you guys are copying this down, I'll tell you an interesting story. I don't know all the details about it, but a couple years ago, it was April 1st, it was April Fool's Day. In Australia, a radio station started broadcasting a bit of an April Fool's joke about dihydrogen monoxide. And they were telling people about this compound that was killing thousands of people around the world each year, and no one knew anything about it. And they just went on and on about dihydrogen monoxide killing people, and dihydrogen monoxide, it's in your house and you should be aware of it, and it's so scary and all these people are dying. And they got all these complaints and people were just getting freaked out about it and flipping out and calling in and being like, how come no one knows about this? Why isn't our government doing anything about this? And it went on for the whole day until the rest of the world that was somewhat educated let these poor radio listeners in on the secret that dihydrogen monoxide was just the chemical name for water. And all these people were flipping out about it. I thought it was pretty funny. Do you want to just throw like, I'm done in chat when you're done these, and then we'll move on. I want to make sure everyone has some time to write them down once we're all done. We'll get going. So often when scientists encounter something a lot, something like water, they give it a common name, and it's generally well understood that the common name among scientists, they'll refer to it as its common name. So if you were to read some fancy scientific study and they used water in it, they wouldn't call it dihydrogen monoxide. They would just call it water. Or if someone is using something, talking about maybe like global warming, and they mention something called methane, well, they don't call it carbon tetrahydride. That's just commonly referred to as methane. So some of these things actually come up in your tests, and they come up in your final exam. There are a few sort of common things that you just need to know what they are, unfortunately. All right, looks like most of you are done. Give you a couple more seconds. So I'm not saying you need to memorize them now. What I'm saying is that you're going to encounter these things a bunch of times, and you'll just kind of get familiar with what their common name is. So you'll see them again and again and again. So we made the joke about dihydrogen monoxide, which is just H2O, which is water. So dihydrogen, H, di means two. So two hydrogens, monoxide is one oxygen, H2O. C6H12O6. We encountered this already when we were talking about biology. Does anybody remember what C6H12O6 is? And then same deal with NH3. We dealt with this when we were dealing with biology as well. It was in the nitrogen cycle. C6H12O6 came up with photosynthesis. And CH4 is just methane, which is one of the ones you just kind of need to know. And we'll talk about it later when we talk about organic molecules. It's a popular one. So dihydrogen monoxide is just water. C6H12O6, that's sugar. When we talked about photosynthesis, we had water, carbon dioxide together. In plants, they make sugar, C6H12O6. CH4 is methane, really common gas, comes all sorts of different sources. And NH3 is ammonia. And ammonia is, again, a super common thing, but we don't call it nitrogen trihydride. It's just called ammonia. All right, a few examples here. N2O3. Does somebody just want to write the name for that guy in chat, and we'll see if we can agree or disagree on it? And SF6. I'm sorry I didn't subscript the numbers, but they should be subscripts. Apparently I missed that. So N2O3, what are we going to call that? We name the first element first, so N is nitrogen, and then oxygen gets changed to oxide. And then how many nitrogens are there? There are two. So what is the prefix for two? If you have a two-wheeled bicycle, you have a bicycle. In science, we call it di. So that's going to be dinitrogen trioxide. SF6, P4O8. Again, this isn't in your notes. I just kind of threw this in as a bonus. I don't know why your notes don't have any examples. See if I can get like a side-by-side going here of these guys. So I can at least just write down my examples. All right, N2O3. I'll supersize this in a second so you can see it a bit better. All right, so let's do these three to start, and then we will move on to the last one, going the other way. So N2O3. We name the thing that's furthest to the left on the periodic table first, and when we write the chemical formula for it, the thing that's furthest to the left will always appear first. So this is nitrogen. Leave myself a little bit of room here. Nitrogen. And then oxygen gets changed to oxide. How many nitrogens do we have? There are 2 of them. So what is the prefix for 2? It is di. So we have dinitrogen. The prefix for 3 is trioxide. So I'm just going to write that again. Dinitrogen trioxide. So that's the first one. Didn't really leave myself a ton of room here. Next one's sulfur. And fluorine gets changed to fluoride. How many sulfurs do we have? What's the number next to the sulfur here? Well, it's a 1. Remember my rule 3. Or no, what rule was it? If we have 1 to start, we never write mono in front of the first thing. We don't do it. So this is just sulfur. And then 6 is hexa. Hexa. Get that right? So this is sulfur hexafluoride. Has anybody ever heard of sulfur hexafluoride before? It's pretty cool stuff. The last one, P408. P is phosphorus. And O is oxygen. Change the ending to "ide." And then we add our prefixes. 4 is tetra on our periodic table, page 5, data booklet. Tetraphosphorus. And then 8 is octa. So tetraphosphorus octaoxide. You've heard a lot about fluoride. Yes. Brush your teeth, Abby. Get that fluoride in there. Sulfur hexafluoride is some pretty cool stuff. I have a little video I'm going to show, and then I'll leave you guys for the day. So that's going from chemical formula to the name. It's really easy once you've practiced it a bunch. They're kind of like gifts. Gifts from the science gods to you, because they're so straightforward. There's no looking anything up on the periodic table if you know the elements fairly well, sulfurs, things. These names are very long. When you get into organic compounds, the names can be like several lines long on a page. It's quite incredible. Whole branch of science dedicated to naming some of these things. So yes, they get very long. There was a few more examples that showed up here in the notes. We had tetraphosphorus, nona sulfide. What's that thing going to look like? We also had tetra arsenic, 2 A's in a row, kind of looks weird. Tetra arsenic decaoxide. So again, these things are gifts. When somebody says, hey, what's the chemical formula for tetraphosphorus nona sulfide? Hopefully you're like, yes, covalent compound, so easy. Don't even need to look it up. So phosphorus, I know is P. So I have phosphorus is P, and then sulfur or sulfide is S. If it's tetra, I look on my little sheet and I see tetra. Well, that means 4. So that means tetraphosphorus, it means I have 4 phosphoruses, and nona is 9. So P4S9 is tetraphosphorus nona sulfide. Same thing here, arsenic, As. Oxide, O. Tetraarsenic. Tetra means 4, so As4. Oxygen is oxide, and deca, I look it up, it's 10. So As4O10. So these things really are quite straightforward once you learn all of the prefixes. And again, when we have all these things individually, we have the multivalent metal question, and then a polyatomic ion question, then a covalent question, all by themselves, really straightforward. When we mix them all together and you have to recognize the differences between these things, that's when they get a little bit tricky. So it's just practice. And the learning guide does not do a very good job of helping you guys practice these things. So that's why I wanted to include some additional questions for you. Let's jump back, finish off the notes here, and then probably call her a day. I wanted to show you guys this video. I think it's really cool. Sulfur hexafluoride, the one that we just looked at, is a really cool compound. And let's watch this little video. How loud is this going to be? Not loud. Okay. Give me a second. My screen's going to go all wonky here, but I promise I'll fix it. Is it not going to go wonky on you? There it goes. Just give me a second. When I move my tablet screen, it does some crazy flipping stuff, and there we go. Here we go.
Hi, my name is James Lincoln, and this is one of my favorite experiments. Everybody knows what happens when you breathe in helium.
The sum of the squares of the legs of any right triangle is equal to the square root of the remaining side.
And many people know what happens when you breathe in sulfur hexafluoride.
We hold this truth to be self-evident that all men are created equal, and that there are no better creators, certainly infinitely worse, and among these are life, liberty, and the pursuit of happiness.
Now, helium raises the frequency of your voice because it's less dense than air. And sulfur hexafluoride is more dense than ordinary air, and so it lowers the frequency of your voice. Sound waves travel faster in helium and slower in sulfur hexafluoride. But what happens when you breathe them both in at the same time?
Happy birthday to you, happy birthday to you, happy birthday dear Einstein, happy birthday to you.
The mixture of equal parts helium and sulfur hexafluoride resulted in an average density that was still denser than that of ordinary air. Therefore, my voice was still a bit lower than normal.
So there we go. Sulfur hexafluoride. Everyone generally is pretty familiar with inhaling helium. Your voice goes really high. It's not very dense. Sulfur hexafluoride is an extremely dense gas, and you end up with a similar sort of thing happening, except instead of your voice going really high, it goes really low. I thought that was cool the first time I saw it. Not a lot of people know about it, so there you go. So where are we at? We finished all of the notes from section 4.2 now, and you should be kind of plugging your way through the learning guide. So the questions you've gone through 4.2 practice, you should be good up to page These are some covalent ones as a bit of an introduction, naming them. And then this is a chart that asks you to identify the differences between them. So we should be good up to here. Today is the 6th. You should be at the end of page 25. Does sulfur hexafluoride occur naturally? I'm not sure if it does or doesn't. I'm not even sure what it's used for, to be honest. All I know is when you inhale it, you sound funny. I'm sure there's some chemical process that utilizes it, else people wouldn't actually make it. So does it occur naturally? It exists in a stable form as sulfur hexafluoride, so I guess it does somewhere occur naturally. That's a good question. I'm not sure. I don't know that much about it. So there we go. We're up to the page 25. Similarly, next week, is it next week already? No. 2 weeks from now, we have our science midterm. So we're going to cut off everything up to that we've learned up to today. So next day when we have class, I'd be happy to answer any questions you guys had out of the learning guide. Be happy to answer anything out of the extra practice that came up. And we'll just keep on moving forward into the balancing chemical equations, which is it next week, Ava? Am I all mixed up? Today's the 6th. If we had 7, yeah, tomorrow's 7th and then 14th. It is next week. Yeah. Mr. Ross is keeping me in line here. It is definitely a week from tomorrow. That makes sense. So we're going to cut off everything up to today that we've learned in science. So you will have to know how to you'll have to know how to form covalent compounds, ionic compounds, biology, and earth science. When we have class next week on Monday, the 11th, we're going to start talking about balancing equations, but we don't have to worry about that for the midterm at the end of next week. Even though it's kind of breaking up the Unit 4 kind of midway, that's okay. I don't want to deal with balancing on the midterm. Everything up to today's class will be on there. So I see you guys twice next week. If we have any questions, we'll go through it, but I don't think anything should be terribly difficult. You have your Heritage Fair stuff for Mrs. Ward for that same 14th, which is next Friday. Apologize for getting those dates mixed up. So I'm going to leave you there. Hope you guys have a great afternoon, great weekend. I won't see you again until Monday. And I'm going to have a study day on Wednesday next week for sure, unless a bunch of people message me needing more than that. So next Wednesday, we'll plan for 1 to 3 again, like we normally did with the math. Wednesday, Mr. Ross, do you know when Mrs. Kitzinger's coming on the 13th? Is it morning, afternoon? Sorry, we have possibly a conflict here. I don't think it'll be that big of a deal, but we'll just let afternoon. Okay. We'll tentatively schedule it for 1 o'clock, and if that has to be moved to Tuesday or Thursday, then we will, but I don't foresee it being that big of an issue. So we'll go with Wednesday next week. And yeah, if you have questions about any of this stuff, midterm, things like that, we can go through that. So Tuesday in the morning? Perfect. That'll work out just fine then. So we'll stick with Wednesday at 1 till 3. For anything science related, or if you want to come hang out and talk about social studies, I'd do that for you too. The midterm's on Friday. And Taylor, you're going to have to do it online. The midterm's Thursday? It's on Thursday the 14th. I'm just all kinds of mixed up here. You guys are both right. Definitely not Friday the 14th, Thursday. Next week, next Thursday. I'm going to stop talking now before I confuse you, myself, Mr. Ross, any further. We're just going to end this. I will see you guys on Monday and have a great weekend. Thanks. You're going to want to sit there and just twiddle your thumbs. Well, I give you a bit of a break here, but it's important to A, become familiar with the periodic table so you can find things really quickly. It's important to B, know how to crisscross your charges or balance out the charges to make the compounds. And just sitting there watching me do it or looking at the answers, it's really easy for you to just sit there and go, okay, yeah, I totally get this. Look how easy this is. But unfortunately, it takes some practice. There are some, things that come up along the way. So I'm going to put maybe like 5 minutes on a timer-ish. And I'll give you guys some time to work. Do as many of them as you can. Don't just stop at the bottom of this page. Keep going to the next page. See how many you can do in 5 minutes. Come back, I'll give you guys some answers, and then we'll look at maybe some polyatomics or something like that next, and see how those are maybe a bit different, or we'll do some questions where we work backwards, where we try to find the charge on the metal to name it, which is trickier. So do as many as you can in 5 minutes, and then we'll come back and we'll look at your answers. All right, guys, welcome back. I was kind of working away as you guys were working away, and I put in some answers. I did them really quick, so if you see something wrong, or if you have a question about how I got to some conclusion that I did, feel free to say something. I did this page, and then I did a few of the next page. So are we okay with what I have there? How did we do? You want to indicate if you're doing okay? Maybe like a thumbs up, green check, something, anything. If you're kind of like, meh, middle of the road, running into problems, or if you're kind of like thumbs down, not doing good, what do we think? These ones can be, pretty straightforward. It's nice and easy if you have the Roman numeral given to you, right? Because you just like, oh, okay, it's a 4, the charge is 4, easy. The second page, Taylor, for sure, gets a little bit trickier because you end up running into some problems and gets a little bit harder. All right, everyone seems to be okay here, so we'll just mosey on down. I'll throw up the answers for these last couple that I didn't show before. And then the next page is one that is tricky. So we'll go through all the answers to the next page. We'll do a few of them together. All right, I've done the first couple for you. That's as far as I got. And my hint a couple pages ago was to make sure you looked at the non-metal. The non-metal charge never changes, and that's going to indicate which one you're using with your metal. Uncrisscrossing the charges will rarely work out well for you. Doesn't matter if I capitalize the element in the compound name. For the second one, I don't think it does. There might be some industry chemistry standard that I'm not aware of that makes you. It's a habit of mine to always capitalize it. I just always get into that habit. So I don't think it's going to matter. It won't matter for what you're doing. Your chemistry 11 teacher might be pickier than me and make you capitalize it or make you not. I don't know what the right answer is. I always do. Maybe you should too. Nobody's ever said anything to me about it in my few years of chemistry, so capitalize it and just go from there. It's nothing to really worry about too much though. All right, so the first one, oxygen had a charge of -2, and there's 2 of them. So because each one has a charge of -2, we have a total charge of -4 to try to balance out with the manganese. So if there's only one manganese and it has to balance out -4 charges, it must be manganese with a charge of +4. It's the only one that can work. The next question is the same 2 elements, which makes it a little bit trickier. Oxygen's always -2, and it indicates that I have 3 of them. So I write down 3 oxygens. Together I have a charge of -6. Manganese needs to balance out that charge of -6, and I know I have 2 of them. So these must be +3 and +3. If they weren't +3s, it wouldn't balance out. Or I would end up with extra positive or not enough positives. When I name this guy, it is manganese. In this case, I've decided that it has a charge of 3. And there you go. Oh, no. All right. RuCl3. I know chlorine is always going to have a charge of -1. And there happen to be 3 chlorines in this example. Ru, I'm not even sure what that name is. It's like ruthenium or something like that. There's only 1. I don't have a subscript next to it here, so I only have 1 of them. And I know I have a total negative charge of -3. So what must this have to balance it out? Well, it must be a +3. So for the ion charge, I'm I'm going to have Ru with a charge of +3. I'm now going to have to find that little guy on the periodic table. Doesn't happen a lot. It is ruthenium. And in this case, has a charge of 3. Chlorine is chloride. Ending chlorine changes to chloride. SNSE, Fe2O3, and CuF2. I'll give you guys a head start. I'm not going to put up a timer, but just give you a head start on the next 3 here and see if you can figure it out without my help. And then we'll go over the answers to the last 3, 4, 5, and 6 on this page. See if you can do it. I have faith in you. SN, SE. Remember, always start with the non-metal. Figure out what the charge on the non-metal is. Figure out how many you have. Then figure out how many you need of the other thing to make it balance, the metal. All right, so those next two, SN, I'm thinking is tin. These Latin names can throw us for a bit of a loop. So SN is tin. Chlorine, selenium, there's one of them, has a charge of -2. There's one tin, it has to balance out +2. So we have tin to selenide. The next one is iron and oxygen. 3 oxygens, each with a charge of -2, is -2, -2, -2 is -6. The iron, or Fe, has to balance it out. There's 2 of them, and you have to end up with +6. So how do I break +6 down into 2 parts? Well, +3 and +3. So that ends up being iron 3. And then oxygen changes to oxide. Hopefully you're right there. The last one, CuF2. I have 1 fluorine, 2 fluorines. They each have a charge of -1, always. Fluorine, my non-metal, never changes. I have 1 copper. It has to balance out the charge of -2, so it's going to be +2. So that's going to be copper to fluoride. So be honest, how did that go? I want to know where we're at. Are we doing okay? Tricky, a little bit lost? Need more practice? One thing that I mentioned last day was that when you are doing these questions, when they're in groups, like they are here, they're really easy. These are all multivalents. We're going to do some polyatomics. These are all polyatomics. Once they get all jumbled up and mixed up, it gets really hard. Because now you need to remember all the rules for multivalence, and then you need to remember all the rules for polyatomics, and then we're going to throw you a curveball with covalence, which have completely different rules, which makes life even more difficult. So individually, they're pretty straightforward. When we mix them up, is when things get hard. All right, so this table has ionic, covalent, and polyatomics in it. And of course, gotta quit doing that. Of course, we haven't dealt with any covalence yet. So that's gonna make life really hard for us because we aren't able to figure out what a covalent is yet. Or we kind of have a general idea, but we don't know for sure yet because we haven't talked about them. So looking at this table, this next page, what I'm going to suggest is the first thing we do is we know how to identify polyatomics. Does anybody remember what we need to look for in a chemical compound that has a polyatomic in it? What's kind of the thing that just kind of makes it stand out compared to just a regular ionic compound or even a covalent compound? What makes polyatomics special? If we can identify all the polyatomics, then we could probably figure out the ionics if we can remember what the rule is. And then by process of elimination, we can figure out which ones are covalent, but we don't know how to name those yet, which is okay. Taylor, 2 capital letters, you're on the right idea. It's 3 capital letters. So if we see 3 capital letters, that means we have a polyatomic. So let's see if we can find all of our polyatomics. So polyatomics have 3 capital letters or more. So I look at my first one, C and O. Well, there's only 2 capital letters there. Mg, Br, M and B, both capitals. Here I have N, I have an H, and I have a C. So that's going to be a polyatomic. There's 3 capital letters there. LiO, that's 2, MnS, that's 2, Kp, that's 2, N and O, that's 2, PCl, that's 2, FeO, it's 2, Mn and O. All right, so in this whole chart, I only have 1 polyatomic on that page. That's an easy start. Ionic compounds and covalent compounds. Does anybody remember what makes these things different? What are we looking for in an ionic compound that we are not looking for in a covalent compound? Or what's special about a covalent compound that I won't have in an ionic compound? A lot of vowels in a row there. Ions? Yes, we will have ions for sure, Abby. When I look at the formulas as they're written here, they don't indicate ions though. You're totally right, ionic compounds have ions, but when I look at the formulas, what is going to make my ionic compound stand out from my covalence or my covalence from an ionic? I'll do my ionics in blue. Ionic compounds are special because they are a metal and a nonmetal. Covalents are 2 nonmetals. So if my chemical formulas that are listed here, this whole first column, if I can find a metal, that makes it automatically ionic. If there's no metal, it's covalent. So this first one, C and O. Carbon, is that a metal or a nonmetal? Oxygen, metal, nonmetal. Those are 2 nonmetals. So carbon, oxygen, both nonmetals, that makes us covalent. The next one, Mg, magnesium. Is that a metal or a nonmetal? Magnesium is a metal, so this is automatically an ionic compound. We will never have a metal in a covalent compound. Just breaks the rules. So what I'm going to do is I'm just going to scan really quickly and look for metals. If I see a metal, it's ionic. Lithium, that's a metal. It's on the left side of the staircase on the periodic table. That's ionic. Mn, manganese, It's a metal. K. It's potassium. It's a metal. N and O, both nonmetals, so that's going to be covalent. P and Cl. P is phosphorus, Cl, those are both nonmetals. Fe, that's a metal, so that's ionic. Might as well finish off this column. Mn, again, is a metal, it's ionic. So these two, by process of elimination, even if I didn't really understand what a covalent was, if I knew what an ionic was, I could eliminate them as being ionic. So this column here, the next column, is the difference between monovalent. Mono is one, valent is charge, or electron configuration, I guess, or multivalent, many electron configurations. So we're looking for the compounds that possibly could have more than one charge. Are there any elements here that have more than one charge? Is it possible to define a covalent compound as being mono or multi? Is it possible to have a covalent compound that has more than one charge in it? Or is that something that doesn't happen? If I look at the nonmetals on the periodic table, these are all my nonmetals over here. Here. Do they have any that have more than one charge? No. All of the multiple charges are like in this middle part. So up here we have all of our nonmetals. They are all negatively charged, and there's not a single one of them that has more than one charge. When we get into the metals here in the middle of the periodic table, we end up with these guys in the middle, the metals, having more than one charge. So I cannot have a covalent compound that is multivalent. It's just not possible. There isn't more than one charge available there. So if I have written in covalent, I can't have a multivalent covalent. That just sounds funny when I say it like that. Magnesium, Mg. Does it have more than one charge? Magnesium, column 2, it only has one charge. So that's mono. NH4 is a polyatomic. None of the polyatomics have more than one charge. Lithium. Find lithium on the periodic table. That guy's in the first column. Only one charge. Mn. Manganese has many possible charges. Potassium, mono. Finish this off. Iron, it's multi. And manganese again. There you go. So this is asking, the third column is asking which charge. If it says multi, like here, which charge are you using? And then we can name all of these things. Well, we can't name them. So let's just do the 3 here. Then we'll take a bit of a break and then come back and talk about some more polyatomics, and then we'll finish off covalence, and then we'll be done this section. All right, so MnS3 is what I'm dealing with. Sulfur always has the same charge. Sulfur is always -2. And I have 3 of them for a total of -6. I have 2 Mn's, and they each have to add together to give me +6. So they must be +3 and +3. So in this case, it's Mn +3. Oxygen It's always minus 2. Iron, in this case, there's only one of them, and it's balancing it out, so it has to be plus 2. Oxygen's minus 2, there's 2 of them, there's only one Mn, so it has to balance out and has to be plus 4. That is the majority of the work there. The next page starts into polyatomics, and I think we'll take a little breather here, and then we will continue on with the polyatomics, which we haven't spent a ton of time looking at yet. So you could do these, and when we come back, I'll have some answers for you. Grab a snack, drink of water, go for a walk, get some blood flowing, get ready to do a few of these questions. Maybe come back in, what do you think? 10, 15? Let's see if you can do these 2 pages, practicing polyatomics. 1 page, 2 pages. Even if you're doing them on a separate sheet of paper that you have, just writing down the answers, that'd be good. So let's put up, let's go with 15 minutes. That'll give you time for a snack, and that'll give you time to do some of these questions, practicing polyatomic formulas. And when we come back in 15 minutes, I'll have some answers, and you'll be full and hydrated and happy, and we'll be ready to go. Thanks, guys. We'll see you in 15. Hi guys, can we go with some green check marks so I know we made it back without technical issue? And you're there live and in person. And then we will go through some of these answers. I'll point out some tricky ones. And maybe you guys can ask some questions if you have any. All right, check marks trickling in. Good to see. So I did these questions, and if you find something wrong with something I've done, again, let me know. One little typo that was in here was, for the second one, it says copper 2 and sulfate. And the symbol it gives you, or the element symbol, Ca, and it should be Cu, not a major thing. Happens that Ca and Cu both have a charge of +2, so not the end of the world, but maybe just check that to make sure you haven't done that. So that's those ones. The ammonium ones at the bottom, a little bit backwards because you're dealing with the polyatomic ion as having coming first, having that positive charge. But there you go. And again, sorry Taylor, just reading your comment. It's really common. I mean, when you're looking at it, you see the 3 down next to it, and then the negative sign up above. You gotta, really remember that that negative is corresponding to -1, even though there's not a 1 there. You have to put in that 1. So, honest mistake. That's why we do all this practice, right? So we don't have to make those mistakes later on. So that was that page. I take it nobody had any questions about that. I named this next group, hoping that you made it this far. And yeah, there you go. I won't really say too much about it. I don't think anything was super duper tricky. I guess these middle ones, 6, 7, and 8, this is the first time you've seen a multivalent metal with a polyatomic ion. So we're taking two of the ideas, putting them together. We hold the same rules when they're separate and together. So if we normally have something like manganese with a 2 after it, even though there's a polyatomic tacked onto the end, we still need to indicate what charge it is. Because obviously these things are really different. MnSO4 looks different than MnSO4-2 and Mn2SO4-3. These are all different looking compounds. They all have different chemical properties. Now, normally we look at these guys and we say, okay, we look to the non-metal to figure out the charge on the metal, because there's more than one charge on that metal. In this case, the SO4 group, SO4, has a charge of -2. That never changes. This SO4 group has a charge of -2. This SO4 group has a charge of -2. It doesn't matter what's tagged onto the front of it. That SO4 group, that sulfate group, never changes. It's always SO4. It always has a charge of -2. In the first example, there's no brackets around it, so you only have one of this group. So if this group SO4 has a charge of -2, the Mn, in this case, has to have a charge of +2 in order to balance the charges out. In the second example, you have SO4 and you have another group of SO4, and each of these has a charge of -2. So together, you have a total charge of -4. So what charge must the manganese have? There's only one of them. Even though I didn't put in a 1, there's only one there. So the Mn must be +4. The +4 and the -4 balance out. Same process here. I have SO4 -2, SO4 -2, SO4 -2. That is a total of -6. I have 2 Mn's, and they have to total +6. So if they're both +3, together that'll give me plus 6. So manganese, 3. Tricky stuff. You guys have the skills to sort it out. The last one's ammonium fluorine gets changed to ammonium fluoride. And phosphite stays as phosphite. Phosphite is a polyatomic, so its ending stays the same. The only example, or there's 2 examples I should say. Number 2 was ammonium fluoride, and that should have been fluorine, but we changed it to ide because it was a nonmetal. But everything else stays as whatever it was. Hydroxide stays as hydroxide. Cyanide stays as cyanide. Permanganate stays as permanganate. Chromate is chromate. Sulfate, sulfate, sulfate. We don't change these endings to ides unless it's just a simple non-metal that we're dealing with here. Does anybody have any questions about any of those? Because they are a bit tricky. No questions? All right. Well, what do you say we talk a little bit about covalence, and then you guys can maybe do some more of these questions, because there isn't a ton of covalent examples in the learning guide or in the notes for that matter. Nope, no questions. All right. Let's jump back to this fella here, and we'll talk about covalence. Now, we've obviously done a few examples of covalence, so we have a pretty okay understanding of what they're going to look like. So here we go. Now, like all of this section, the notes in the book are just not good, but I didn't want to change them up because it's just easier to do it this way. So what I'm going to do is I'm going to go through the notes that are given in the book. When I say book, I mean learning guide and the course. And then I'm going to add some additional Mr. Borden's rules, which should hopefully help to clarify things. So covalent compounds or molecules, I would say they're easier than ionic, and I'll show you why that is in a second. When you end up with a covalent on a test or a quiz, or you see it in an example, it's kind of like a gift because they're really easy to deal with. But that really easy means that you have to be able to identify when you're dealing with them. So that's kind of the only catch here. If you can identify that you have 2 nonmetals, you're dealing with a covalent compound, then they're easy once you learn the rules. So names may reveal the components, but often do not. We still have subscripts with these guys, and in ionic compounds, we always reduced. We always went to lowest terms. In covalent compounds, we don't reduce. If it is CO2, that means there's 1 carbon and 2 oxygens. If you have CO3, that's a different thing. If you have CO, that's different. So we don't reduce the coefficients when we deal with covalent. If we put a 3 after something, that means there are 3 of them there. It's not like ionic compounds that form these big lattice structures where there's thousands upon thousands upon thousands of these atoms kind of all bonded in this nice lattice block-like structure. When we form a covalent compound, we form it, it lives by itself, there's just 1 of them. So we'll show you why that's important here in a second. I don't know why C2H6O comes up here and why they make such a big deal of it in the notes, but they do. So there you go, that's sucrose. C2H6O, I'm thinking that's, no. That's a type of sugar, but I can't remember off the top of my head what sugar it is. I don't know why it's important. It doesn't really come up that much, so I wouldn't worry about it too much. So here we go. When we deal with covalent compounds, we use a system of prefixes. So pre means before. So if we're dealing with something like carbon, if we have more than one carbon, we'll put a number in front of it. Instead of it being like 1 or 2 or 3, we use the prefixes mono, di, tri, tetra, penta. Hexa, hepta, octa, nona, deca. And these guys are actually in your periodic table. Or not your periodic table, they're in your data booklet. They're on page 5, right next to your polyatomic ions in your data booklet. So they're all there for you. You don't have to memorize them, which is great. So they're just in a small little table next to your polyatomic ions on page 5 in the data booklet. So that's kind of nice that we've included that. You don't have to memorize any of them. So this is what I was speaking to before. When I have something like CH4, that's 1 carbon, 4 hydrogen, we call it methane. That's a C and an H together. In an ionic compound, if we have something like sodium and chlorine, there's only one way to combine these things. 1 sodium, 1 chlorine, electron gets transferred, they stick together, sodium chloride. That's it. There's only one way to do it. When we deal with covalent compounds, there's many ways for these things to bond together. So CH4 is methane, C2H6 is ethane, C25H52 is candle wax. So we can have these really, really long chains of carbons, and hanging off of them is a bunch of hydrogens, and we can just make them bigger and bigger and bigger. And they're really common. And there's lots of everyday things that are hydrocarbons, which is what we're talking about here. So the element changes, even though it just has the same I shouldn't say the element changes, the compound changes depending on how many atoms are there. So we have CH4 and C25H52, different things. CO2, carbon monoxide, CO, carbon monoxide, CO2, carbon dioxide. These are things that are different. 1 carbon, 1 oxygen has different chemical characteristics than 1 carbon, 2 oxygens. They are different. So this attempts at coming up with some rules for naming these things, but it does a very poor job of it. So what I did was I came up with my own rules. So we'll look at an example, then we'll look at my rules, and then we'll do some more examples. So what is the chemical formula for the molecule trinitrogen tetrachloride? This is why covalent molecules are really easy, because I don't have to really look to the periodic table. If I can remember the symbol for nitrogen is N, chlorine is Cl. When I look at it, it says trinitrogen. So tri, like a tricycle, 3-wheeled bike, trinitrogen, 3 nitrogens. Tetra, something that may not be quite as obvious to you. If you look at your chart, tetra is a 4-pack. So tetra is 4. So we have trinitrogen is 3 nitrogens and 4 chlorines. So what is that going to look like? Does it not even write it? It doesn't even write it. That's maybe an omission on mine behalf, or maybe it's just not in the notes. But it should somewhere say N3Cl4. I don't know why it doesn't. Let's add it right now so we don't get confused. Can't even edit that. All right. See if I can do this. Nitrogen, I'm not going to put in my subscripts, but it should be trinitrogen, so N with a little 3 after it. I'll supersize this in a second. And then Cl with a 4 after it. Cl4. That should be subscripts. So let's make them subscripts. Oh, it's down there, but it's not on the... Maybe I'm just losing my mind. I don't know. I thought I didn't see it on this other page. Maybe it was there. Maybe I just need to... Yours has it. Okay. Perfect. Mine didn't, and it was in the other page. I don't know why it's not showing up here. I think it's kind of hidden, maybe back here or something. You guys are on it though. All right, so there you go. That's that guy. The next one is Si3P6. So Si, name the metal, Si silicon. P is phosphorus. Find the prefix. So 3, if you look at the chart, 3 is tri, and 6 is hexa. So you know most of these bigger ones. If you talk about a hexagon, that's a 6-sided shape. If you talk about an octagon, 8-sided. Nonagon, 9-sided. So you guys have run into these prefixes before. This isn't the first time you've seen them. So 3 is tri, 6 is hexa. So this is tri-silicon hexa phosphide. There you go. So those are two kind of examples to get your feet wet there. Here are my rules, and these will work for almost all of them. CO and CO2 are both covalent compounds. They're very different. CO is carbon monoxide. CO is a scentless, odorless gas. People get it in their houses a lot. You have a carbon monoxide detector in your basement, maybe, if you have like a gas furnace. It's deadly gas. It'll fill up your basement, and your body has a difficult time telling the difference between CO and O2. So you inhale a bunch of carbon monoxide, and you can just basically fall asleep and die. And people die of carbon monoxide poisoning all the time. CO2 is a byproduct of burning things. When we exhale CO2. They're very different. Carbon monoxide, carbon dioxide. They're different things. This isn't in your notes, but you should write it down. I don't know if you have room somewhere there.